Alright, in this video we're going to take a look at the problems in homework assignment number 10. These have to do with designing filters, and I have up here the web page for homework assignment number 10. I want to point out that at the top of the page you can click on this link and get the slides on filter design that we were talking about in a previous video. So let's jump in and take a look at these problems. There are 4 problems, and we'll go through each one of these in turn. So in the first problem, we're going to design a band pass filter, and the specification is given here. There's an amplitude part of the specification and a frequency part of the specification. If you take these numbers, you should be able to combine this and draw a picture. We'll take a look at that picture in just a minute. But you can see that the first specification here requires that the magnitude response be less than 0.01. This is a very small number, so we would consider this a stop band. And it extends over these frequencies. With the absolute value here, we're including positive and negative frequencies. Here's a band where the magnitude response is constrained to lie between 0.95 and 1.05. So we would consider this a pass band, since the gain is usually pretty close to 1 in that band, and the band of frequencies you can see here extends from 0.75 cycles per sample to 0.3 cycles per sample. And then finally, here's another band that looks like a stop band because the gain is very small, and here are the frequencies. If we take that specification, we can come over here and draw a picture. This is the picture that I'm referring to here. And we'll go through the rest of this in just a minute, but I want to focus your thoughts here and help you recognize that anytime you're designing a filter, this is a good time to get out a piece of paper and a pencil and actually sketch out what the response looks like. Sketch out the bands, the frequency band edges, sketch out the pass band, stop band, the attenuation, and so on. So if we translate those specifications we saw on the previous page in the problem statement, we can draw this picture. Here is a stop band, and so we require that the gain in that stop band lie between 0 and 0.01. There were 2 bands where that was required. There was one at low frequencies, there was another one at high frequencies. I'm only sketching the positive part of the frequency axis. The negative part would be a mirror image of this. And then there was a pass band between 175 and 0.3. That's pictured here, and the response is required to be between these limits in that set of frequencies. So the part that's shaded in yellow, that's the envelope where we want the magnitude response to be over that band of frequencies. And the other thing that I'd like to point out here is that there's been no requirements placed on the magnitude response in these transition bands. And so generally we'll want to see a decay in the response between the bands, or a gradual transition between the 2 bands, but the specification makes no claims about what the magnitude response has to be out here in the transition band. Let's see, if we go back now and look at the problem statement, it says, design this filter using the window technique, using the best window from the set rectangular, Bartlett, Hahn, Hamming, or Blackman. Those are the window shapes that are given in this table. And so basically we're supposed to select from among the windows provided in this table. The second part says use this design this filter using the window technique, using the Kaiser window. Again, we can go back to the recipe page, and we can pull up the charts that talk about how to design using the Kaiser window method. And then finally, we'll bring up the filter designer tool in Matlab, and we'll design this filter using the equal ripple filter design technique. Then it says, make a table with 1 row for each filter you design. The table should have a column for the following parameters: the length, the order, the group delay, the type of filter, and the window parameters, such as the beta parameter for the Kaiser window. and the window shape for the other window. Then it says, for each filter you design, turn in plots of the impulse response, the magnitude response, the phase response, and then make a pole zero plot. Okay, so let's jump in and take a look at the first part here using the windowed filter design technique. Let's go back and review the recipe for the window filter design technique. What we do is we begin with our specifications. Let me take you back one page to see what those specifications are. We could be given specifications in dB in the pass and stop bands, or we could be given the error ripple magnitudes in those two bands. And then using these formulas at the bottom of the page, we can convert from one to the other. We also should be given the pass and stop bound edges, and from those we can calculate the band center frequency and the band width of the transition band. So we'll start with the magnitude specifications, and we'll make a decision about the window shape based on the amount of ripple in the bands. Then we'll use the window shape to look up a constant that's related to the window length. We look that constant up in the table. That comes from this column here. And we'll use the bandwidth of the transition band and that constant from the table to calculate the length of the window. In each case, we'll need to figure out what's the ideal impulse response before we apply the window. And then finally, we'll calculate the window and apply it. Let's take a look at how this is done. Okay, so here for the windowed filter design method, I've written down the filter specifications in the two bands. We have the stop band attenuation is 0.01. That can be converted into 40 dB specification. And in the pass band, we have a 0.05 error specification. Using the formula on the chart, we can convert that into a parameter in dB. The next step in the table, or in the recipe, if we go back to the recipe for a minute, is to choose the minimum of the two error parameters, and then from that calculate the A parameter. So we'll choose the smaller of the two error parameters, so we're comparing 0.01 with 0.05, that gives us a 0.01. If we convert that into a specification in dB, that gives us 40 dB. We'll take that into the table, look at the last column, and that says that we need at least 40 dB of attenuation. It looks like the Hahn window will provide 44 dB of attenuation, so we'll go with the Hahn window. Then we calculate the transition bandwidth, because in this case it's a bandpass filter. We have two transition bands. We have a narrow band and a wide band. So we end up choosing the smaller of the two bands. 0.05 then will be our transition bandwidth. We'll convert that into a bandwidth in radians and plug that into the formula. Where does this formula come from? Well, again, we'll go back to the chart. We've selected the window shape. Now we're calculating the window length, and there's a formula here for the width of the transition band in terms of the length, but it depends on a constant. Where does the constant come from? Well, that comes from the table. So if we go into the table on the row for the Hahn window, the constant is 6.2. So we bring that constant back to our formula here. We plug in the numbers and we calculate that the length of the filter will be 62. The order M of the filter will be 61. That's an odd number, so this is a type 2 filter. Now we need to calculate the impulse response. This impulse response, a sinc function, is for a low pass filter. So what should it be for the band pass filter? Well, we can calculate by averaging the edge frequencies. We can calculate the center frequency of the transition band in both cases, and then with those numbers, we we sketch a dashed line which represents the frequency response of the ideal filter. So I've drawn that here as a dashed line. So that's the ideal frequency response. Over here I'm doing a calculation where I'm computing the inverse Fourier transform of the ideal frequency response. So you can see this is just nothing more than plugging into the inverse DTFT formula. And when all is said and done, we get the difference of two sinc functions. So let's go over to Matlab now and see what this would look like in Matlab. So in Matlab, I'm plugging in the filter specifications into a vector. I calculate the smallest of those specifications and then calculate the dB quantity A. Then I calculate the width of the transition bands. I take the smaller of the two transition bands and I calculate the center frequencies of the two transition bands. Next I make a decision about using a Hahn window, and then I plug into this formula for the length that's required for a Hahn window. And then I calculate the order and the group delay. The group delay will always be 1/2 of the order for these linear phase filters. And then finally I will calculate the Hanning window or the Hahn window. Let's run this much code. All right, we'll try that again. Okay, now scrolling down, we need to calculate the impulse response of the ideal filter. And remember, as I said over here, it's the difference of two sinc functions. So we'll plug that into MATLAB's, I'm going to use MATLAB sync function here. And notice that the n values that are plugged in are equal to 0 to m, 0 to the order, and then I subtract the group delay. That's what gives this phase, or this filter, a linear phase response. And so if I do that, maybe we'll apply the window at the same time. Let's just take a look at these. Let's take a look at a few things here. So first I'm going to say stem HD. This is the impulse response of the ideal filter. There it is. It's a difference of sinc functions. Let's also stem the windowed filter. There it is. Notice that in the tails, the impulse response tapers down. That's the result of applying the window function. Let's also plot the window so we can see what that looks like. And here is our Hahn window. Not too much to say about that, but other than the fact that in the center there's no change to the impulse response, but as we get towards the tails of the impulse response, applying this window by multiplying by the window, that will tend to make the impulse response values taper down. So that completes this portion of the design. Next, let's move on to designing the Kaiser window. The recipe for the Kaiser window looks a lot like the regular window method, but instead we're going to take the parameter A and plug it into this piecewise defined function for the parameter beta. And it looks like, let's see, our A value is 40 dB. So if we look at which case this belongs to, it looks like it's this middle case. So the function that I need to evaluate here is I need to plug A into the middle two lines of this piecewise defined function to calculate the beta parameter. And then to calculate the order of the filter, we'll plug into this formula down here. Let's see what that looks like. So here's our calculation for the beta parameter. Again, I'm plugging 40 dB in for A. and it looks like I get a beta value of 3.3953. Also, I'm plugging A and delta omega, the transition bandwidth in radians, into the formula for the order, and I get an order of 45. That's an odd number, so this is a type 2 filter. That should be just fine. And so remember, a type 2 filter has a required 0 or a null in the frequency response at 1/2. And that's not going to be a problem here because this is a bandpass filter. So the Kaiser window will use a filter of length 46. If we just stop here and compare, the basic window method uses a filter of order 62, and the Kaiser method uses a filter of order 46. So we can see that we're already getting a little bit of a savings by using the Kaiser window method. Let's go back to Matlab and see what this looks like. Again, you'll recognize these formulas as being taken from the recipe page, and let's go ahead and paste those into Matlab and calculate the Kaiser window and apply that to the impulse response. Let's do a hold on and plot the Kaiser window, W, and just compare the Kaiser window to the Hanning window that we previously plotted. You can see that they both leave the center of the impulse response unchanged, but now there's a different tapering behavior when we get close to the tails. Notice that for each filter we design, there's a different length m, and so we'll need to generate a new set of time samples, and we'll also subtract by a, which is the group delay. That gives us the impulse response. So if we do a plot H Kaiser and hold on and then plot H Win, this shows us our two impulse responses for these two different filters. Okay, they look a lot the same in the center, and that's as we would expect because the window function doesn't change the center coefficients very much, but they do differ as we get into the tails. The other thing that's very different is the length of these two filters. So the Kaiser window, we're not going to have to work as hard calculating the output of the Kaiser windowed filter because it's shorter than the Han windowed filter. Okay, now let's go and design the equi-ripple filter using the filter designer tool. And I'll show you an example of how we would plug this specification in. So first of all, we're going to select FIR equi-ripple, and we'll do a band pass filter. The sampling rate will be 1. The stop band edge is 0.125. Pass band edge is 0.175. The upper edge of the pass band is 0.3, and then the stop band starts at 0.4. Let's see, in the stop band we have let's see, we're going to put our specification in linear units. So our stop band edge, or our stop band error can be 0.01. This in the pass band can be 0.05 and then 0.01 in the other stop band. We'll select minimum order filter design, and then we'll just say design the filter. And it looks like it believes it can achieve the specification with a 29th order filter, so the length would be 30, and that's even less than our Kaiser designed filter. So we've got a length 60 filter, we have a length 46 filter, or we have, if we use the equi-ripple filter, one that's length 30. A pretty remarkable difference. Here's a picture of the impulse response. Here's the phase response, magnitude response, pole zero pattern. We might have to zoom in on that to see what the, zoom in close to the unit circle to see what's going on there. But that's something we could look at. In fact, I want to look at that. Notice that we have zeros in the stop band, the low frequency stop band. We also have zeros in the high frequency stop band close to the unit circle. And then in the pass band, we have these zeros away from the unit circle. That allows the response to come up and receive kind of a unity gain in the middle of that pass band. What's pulling it up? Well, the poles at the origin are pulling the response up in the pass band. One other thing I want to point out here, notice that the passband edge is at 0.3, which is right here. The units are millihertz, and so this is at 300 millihertz, that's 0.3. And then the stop band starts here at 0.4. And in the transition band here, notice that we see this rise in the response before it comes down. And that's a result of the fact that we haven't put any constraints on the filter in this transition band, and so we allow the filter to do anything it wants to do in that band. So that's how you would design it, and if you wanted to implement this one, you would just say export that filter to the workspace as coefficients, and you just export those numbers. If we were to do that and we said stem num, this is the impulse response of that filter. Notice the symmetry, because the order is 29. The center of the filter, the point of symmetry is at an integer plus 1/2 rather than on an integer. Okay, so we're done with that. Let me take you back into the programmatic part of Matlab and show you another way that this could be done using function calls. So Matlab has a function built in called FIR PM ord. So FIR PM is the function that is called by the filter designer internally when it's designing an equiripple filter. FIR stands for finite impulse response filter, and PM stands for Parks and McClellan, and these are the two individuals that figured out the algorithm for designing these kinds of filters many years ago. Tom Parks and Jim McClellan. So FIR PM ord, this is an order calculating function, and all we do is put in our filter specification to this function. If we come back to Matlab and type help FIR PM ord, we can learn how to use this function. It looks like it takes several things. One is a frequency specification, an amplitude specification, a set of numbers that represent the deviations that are allowed in the different bands, and then the sampling rate. Let's take a look at how we've entered those numbers here. So here I've entered my pass band and stop band edge frequencies. I've also entered what the amplitude response should be in those bands. Notice that the magnitude should be 0 in this first band, 1 in the second band, the pass band, and then 0 again in the stop band. So this is how you tell Matlab what you want the magnitude response to be in the different bands. And then here I'm plugging in the deviations that are allowed by our specification. Then last but not least, I'm plugging in a sample rate of 1 sample per second. I guess when I wrote this script, I didn't want a. Let's actually just run this and see what we get here. Okay, so the order that was returned is 29. Notice that's the same number that was given to us from the filter designer tool. It's also returning some other parameters that can be passed into the FIR PM function. So we don't need to pay too much attention to that. But apparently when I first wrote this script, I decided that I didn't like the type 2 filter. So I'm going to add 3 to that, and that's going to turn it into a type 1 filter. Because let's see, 29 plus 3, that's 32. M is even, that's a type 1 filter. So if we run this, then we get our filter impulse response. I have a special function that I wrote to make some plots of the different responses. Here you see the pole zero plots for the window, Kaiser, and equi-ripple method. Here are the phase responses for the three different methods. Notice that the phase responses have different slopes, and that's because they have different group delays. But they are linear phase in the passband, or in they're linear phase filters. And don't need to talk about that too much right at the moment. But notice the magnitude response here. I guess we'll look at it in dB instead of on the linear scale. You can see that all of these filters meet the specification. Let's zoom in on this just a little bit. I'm going to zoom in on positive frequencies. And you can see that here we are at 0.175. All of the filters give a response below 40 dB. The windowed method has let's see, with the Hahn window, its side lobes decay as you move away and deeper into the bands. You can see that here. And let's see, also, why does the equi-ripple filter give us this extra notch? Well, again, that's because, remember, our passband specification said we have to transition from the passband edge at 0.3 to the stopband at 0.4. And the filter designer tool is free to do that in any way that it wants to. Notice that by the time we get to 0.4, our filter response for the equi-ripple filter is indeed below 40 dB. So we do, even though it looks a little bit weird, it meets the specification. And then here are the impulse responses. Once again, you can see that the windowed method gives you a long response. Kaiser gives you a shorter response, but the equi-ripple filter gives you the shortest. And so some people would prefer the equi-ripple method over the others. Okay, let's go on to the second problem. We'll go a little bit more quickly now. In this problem, we're going to design a filter, a low-pass filter, with a very narrow transition band. Notice that the pass band is between 0 and 0.24. The stop band is between 0.26 and 0.5. So if we take that specification, also we have ripples specified in the two different bands, 0.1 dB in the pass band, 60 dB in the stop band. And if we come over here and make a picture of that filter, this is what it looks like. The interesting thing about this filter is that the transition band has to be really narrow. And so we have to roll the filter off from the pass band to the stop band over a very narrow band of frequencies that is 0.02 cycles per sample wide. If we take the parameters that are given and plug those into the recipe, we can calculate that the stop band specification is the dominant part of the specification, and that requires 60 dB of attenuation. If you go into the table, you'll find that only the Blackman window provides the level of attenuation that's needed in the stop band. And so we'll use a Blackman window for this, and the length constant that we'll be using is 11. So we plug that into the formula to calculate the length. It looks like we need a fairly long filter. Again, why do we need such a long filter? Well, remember, the width of the transition band depends upon the width of the main lobe of the window. How do we make a narrow main lobe? You have to have a long filter in the time domain. So anyway, we plug into the formulas and we calculate that the length is 275, the order is 274. That's a type 1 filter because it's an even order. Then we plug in, we take the ideal impulse response, and we do the inverse discrete time Fourier transform to calculate the impulse response in the time domain. Then we go back and do the similar sort of thing for the Kaiser window method. I'd encourage you to use the recipe, plug into the values there, and see if you can calculate these same numbers. Let's go back into Matlab and see what this looks like. Again, it's very similar. I just plug in the specifications as before, calculate the type of window that will be used, and then I evaluate the window or the impulse response, design the window, apply the window, and then the filter is done. It's designed. Similar sort of thing for the Kaiser method. Just plug into the appropriate formula, compute a Kaiser window, calculate the ideal impulse response, and then apply the window. Same thing for the equi-ripple filter. We'll plug those parameters in to the order estimator, or you can go back into the filter design tool and get some experience designing filters using the filter design tool. So I think I've said enough on that second problem, and I'd like to move on to problem 3. Again, each of these problems requires you to make plots of the magnitude response, record your filter designs in a table, and so on. Okay, in problem 3, we're going to design a low-pass filter to be used in sample rate conversion. And we're going to change the sampling rate. We're going to go up by a factor of 3 and then down by a factor of 4. We'll also note that the input signal has a maximum frequency of 1/3, and we need to design a low-pass filter to meet these specifications. 0.1 dB ripple in the pass band, 60 dB of attenuation in the stop band. It also says, use your knowledge of upsampling and downsampling to determine the pass band and stop band edge frequencies. So for this problem, let's go back and think about sample rate conversion. This is a block diagram of the system where we take a signal x of n, we upsample by 3, or we insert 2 zeros in between each good sample. Then we fill in those zeros with a low-pass filter. That low-pass filter also avoids any aliasing that can occur when we downsample at the end. I've also made a note that the input has a maximum frequency of 1/3. So let's go and make a picture of what the input signal looks like. Here it is, plotted from -1/2 to 1/2. I'm using a triangle to represent the magnitude spectrum of the input signal. And so it extends from -1/3 to 1/3. When we upsample, you recall that what happens is we scale the frequency axis by a factor of 3. So the frequency that used to be at 1/3 is now at 1/9. Also, remember that this I'm only plotting one period of the Fourier transform. There's really another period that looks just like this one with the triangle centered at 1. When we divide those frequencies by 3, that triangle that's centered out at 1 in the next period scales and comes down to be centered at 1/3. A similar sort of thing happens at negative frequencies, giving rise to this triangle centered at -1/3. So this is the magnitude spectrum of the signal going into the low-pass filter. Once we understand that this is the signal that needs to be filtered, we can select our pass band frequency and our stop band edge frequency. Here it's pretty obvious what we should do for these two frequencies. Notice that we want to pass the frequency 1/9 and all frequencies less than 1/9. And we want to eliminate this image over here, this upper triangle and lower triangle. And so that suggests that our stop band frequency, our stop band edge, should start at the frequency 2/9 and extend all the way out to 1/2. So I've gone ahead and drawn a specification based on those considerations. And we also know we've been given amplitude specification parameters for the pass band and stop band. Once we have the frequencies specified, we can calculate the center frequency. And we also know that the transition bandwidth is 1/9. I've also gone in and sketched using a dashed line what the frequency response of the ideal filter looks like. After we apply the filter to this input signal, this is the signal that is resulting on the output of the low-pass filter here. Notice that the maximum frequency is now 1/9. When we downsample that by a factor of 4, that frequency at 1/9 gets scaled by a factor of 4 and becomes 4/9. So this illustrates what's happening in the frequency domain as we step through the stages of this processing. Let's go back now and think about when we were first discussing sample rate conversion. We were only ever thinking at the time about ideal low-pass filters, not practical filters that have to have transition bands and ripple. When we were talking about ideal filters, we argued that the cutoff frequency for the low-pass filter after upsampling should have a frequency that's 1/2 times the upsampling factor. So that would tell us that the critical frequency for this low-pass filter is 1/6. When we're doing downsampling, a similar consideration says that before we downsample, we need to low-pass filter to prevent aliasing when we downsample. And the critical frequency for downsampling was 1/2 times the downsampling factor, 4. That would suggest that the cutoff frequency of the ideal filter should be 1/8. In a combined sample rate conversion process, as shown here, we decided that we would select the cutoff frequency to be the lower of the two upsampling, based on consideration for upsampling and downsampling. That would suggest a cutoff frequency of 1/8. I've gone ahead and drawn in that critical frequency of 1/8 here, just so you can see where that is on the frequency axis. Notice that our considerations, now that we understand how to design practical filters, give us additional information on how to select that filter. It looks like we're going to be just fine with the practical filter that we get from the filter design methods we're aware of. And so these earlier considerations are now sort of taking a back seat to our understanding of filter design and our understanding of sample rate conversion. So again, following the recipe for windowed filter design, we have a stop band attenuation of 60 dB that requires a Blackman window. And given the transition bandwidth of 1/9, we calculate that we need a window of length 50, a filter of length 50, or an order of 49. That's a type 2 filter. We can also plug into the Kaiser recipe and calculate the beta parameter that we need and the filter order and length. And again, that gives us a type 2 filter. Using the knowledge of the cutoff frequency, which is 3/18, we can plug in and calculate the impulse response of the ideal filter. This, of course, will need to be delayed and windowed before it gives us a practical filter. So we can go back over into Matlab and look at how this is done. This is now going to start looking very familiar because we just plug in the specifications. We plug into the formulas, we design a window, we evaluate a time sequence and evaluate the ideal impulse response, and then finally apply the window. That's all there is to it. Same thing is true for the Kaiser method. And then with the equi-ripple filter, we can either use the filter designer or plug in to the filter designer software programmatically as shown here. I think that's enough said on problem number 3. Let's now go on to problem number 4. In problem number 4, we're going to design a filter that boosts low frequencies by a factor of 4. Low frequencies lie between 0 and 150 Hertz. And then we want to leave the scale of the frequencies above 300 Hertz unchanged. So this is a shelving filter, and notice that there's really no stop band in this filter specification. We have 2 pass bands. One pass band extends from 0 to 150 and has a gain of 4, and the other passband goes from 300 to half the sampling rate, and that has a gain of 1. Well, we're told that the sampling rate is 20,000 samples per second. So we have to convert all of this information into a filter design specification in discrete time. So again, the first thing I like to do is make a sketch of the given information. So here I'm showing two passbands. One has a gain of 4, and that extends up to 150 Hertz. And then there's another passband that goes from 300 Hertz out to 10K, which is half the sampling rate. And that has a gain of 1. We can convert this into a discrete time specification by just rescaling the frequency axis. If we divide by the sampling rate, where Fs is 20,000 samples per second, we get normalized frequencies. So I'm not calling this F-pass and F-stop anymore because these are both passbands. So I'll label these frequencies as F1 and F2. We can calculate the center frequency. We can also calculate the frequency transition bandwidth. The ripple specification given in the problem statement is delta equals 0.01 in both bands, and that leads to an A value of 40 dB, so we can use the Hahn window. Again, if we plug into the formulas, we find that with an Hahn window we'll need a filter of length 415 coefficients, or 414th order. That's a type 1 filter because M is even. If we plug into the Kaiser window recipe, we'll find that beta is 3.3953 and that the filter order is 298. So it's considerably shorter than the Hahn window. The last step is calculating what the impulse response of this filter should be. So I've gone ahead and drawn as a dashed line the magnitude response of the ideal filter. And if we calculate the inverse Fourier transform, we find that that's 3 times the sinc function plus delta. How did I get that? Well, this is the definition of the ideal filter, the frequency response. It has a gain of 4 over low frequencies and a gain of 1 at higher frequencies. I can decompose this into 2 ideal filters. One has a gain of 3 and 0, and one has a gain of 1 for all frequencies. So if you calculate the inverse Fourier transform of these two parts, the inverse Fourier transform of 1 is delta. And the inverse Fourier transform of 3 and 0, that's just a low-pass filter, is 3 times a sinc function. Recall that when we add the delay to get linear phase, that's going to create a delay of the sinc function. There's no problem there. But when we delay the delta function, we cannot delay by anything other than an integer. So here alpha, which is the group delay, must be an integer. That requires that the filter order be an even number, and that means we have to have a type 1 filter. Fortunately, the filters that were given are type 1, and so they'll have a group delay alpha that's equal to an integer. Going back into Matlab, this problem data can be plugged in as shown here. Here's for the windowed method. Notice that if I find that that m is an odd number, I'll go ahead and add 1 to make sure it's even, so that the group delay is a linear function, or is an integer. Here I'm evaluating the Hanning window, and I am evaluating the sinc function, and then to get a delta function, I'm just adding 1 to the center coefficient. That's like adding a Kronecker delta. Here I'm applying the window to that impulse response. The Kaiser method is very similar. And And then last but not least, we have the equiripple method. Notice that we have a pass band and a stop band edge. We have a gain of 4 and a gain of 1, and we pass in the ripple specifications and state that we have a normalized sample frequency of 1. All the rest of this is plotting. So I think we're done. I think we've now talked about all of the different problems here for this homework assignment. There is a 5th problem that says, after working the previous 4 problems, summarize your observations about the best filter design method to use if the goal is to minimize the filter length. Well, as we've stepped through here, we have seen that the window method generally gives us the longest filter. The Kaiser window gives us a shorter filter. We can see that's true in each of the cases we've looked at. But here the Blackman window was length 50, the Kaiser window was length 34. And also in these examples, you'll find that the equiripple filter will in general give you an even shorter filter than even the Kaiser window. And so that's the idea that you look at as you're thinking about your answer for this last problem.